the joint law of x and y, we can write it down as the integral over the set B, and then we have some density function here, some function. And now I write x and y there, and I write the two-dimensional Lebesgue measure dx dy in this way. And now we should look that, okay, there are different ways of writing this integral. So we might write it's an integral over the r squared. Then we have this function fxy, and then we have indicator b. And then we have the two-dimensional Lebesgue measure. So this way, that would be the short way of writing this. And then when we know that the Lebesgue measure is defined on the Euclidean plane, so we can take this way when we integrate over the full space. Okay. And the key thing is that we assume that this is true for some Borel function fxy, which maps the Euclidean plane into non-negative numbers. That's if we assume that this is the case, then we write that then this is called a joint density. Let's say a joint density of x and y. Some random variables admit a joint density, some do not. If we have a joint density, let's do one theorem. So if fxy is a joint density of x and y, then how could we obtain a density for fx? In the usual way, we define fx to be the integral of the fxy. Now we keep x fixed and we integrate out the second coordinate, so with the Lebesgue measure. So then this, and of course the same thing for y. So these are the formulas that you have probably seen in many earlier courses. So if you integrate out the first variable now in this way, so then these are densities of x and y respectively. And yes, I hope I didn't miss anything. Yep.
Should the second one say dx?
Yes, thank you very much. It should, of course, we integrate x away, and that's what we do. How to prove this in our current setting up with the Lebesgue measure proof? Let's see. What we want to do, we want to look, okay, what we want is actually that we can represent the law of x1 using this density fx, this type of function. And let's look at how does the law of x1 behave. So let's take some Borel set here. This is a usual Borel set of the real line, and then let's see what this gives us. So again, we used the fact that this is obtained from the full law of the, okay, let's see, x was now the first coordinate, so we use the full law x, the law of x and y, and then we had this b1 and then the full real line here. That was the connection with the joint law and the marginal law. And now we know that we can write this as because the joint law has density. So now we write this as an integral over b1 times r. And then we use this density of the joint law here. And the bivariate Lebesgue measure. And then what do? We know that fxy is a non-negative function. It's a measurable and non-negative. And now we need to kind of figure out, we also remember that this is a product measure. So we have learned about product measures in the previous lecture using the Fubini's theorem. So we apply Fubini, F for Fubini, or maybe Tonelli might be in place here. So we can write this using two integrals. And then we can write fxy there. Well, we don't do anything here, but we just write this as a collection of two integrals. So let's put here lambda dy and lambda dx. According to Fubini, when we have a non-negative integrand, it doesn't matter in which order we integrate. So let's choose the order that we first integrate with respect to y and then with respect to x. Both integrals here are across the real line. So that's the Fubini's theorem. And that's why we can do this nested integral. Yeah. Then what? Well, what's inside? Integral where we integrate with respect to y variable. How did we define fx of x? Well, we define it as the integral with where we integrate out the y variable. So this fxx here is precisely, if we go down here, it is this one there. So this one here is what we just decided to call fx of little x. Yep. So because we call it with that name, let's use that name then, that we use to baptize this function. So we write it as, there's something wrong again. I'm sorry. Today is a high mistake density. Can you see where's the mistake here?
That should be B1, the outer set that we are integrating on.
B1 is gone. B1 should be there, of course. So B1 is there. Yes. And now we write it as integral over B1 fx of x lambda dx. And this is true. What we have here and what we have there. This is fine for all Borel sets B1. So that's the end of the proof for fx. We can represent the law of random variable x for every Borel set, so we can represent it as an integral with this function. So that's what it means that this function is a density as we want it. And that's why we have proved that this one is a density for x. The second case is just symmetry. Do you have questions about this one? Fubini's theorem is a wonderful tool to make these conclusions. And in a way, if you do probability theory, you might use Fubini kind of every day in your research. It becomes kind of automatic, so you might not actually even think about that you are using Fubini. It's you just do it. But to be able to do it, you need to know that your integrand should be either non-negative. So in the non-negative world, you can change these integrals, or you should first check that your integrand is in L1 with respect to the product measure, and then you can do things what you want. Otherwise, you may actually run into trouble. And that was the fact here.
I have a question related to these theorems or proofs per se, but the differential when we're integrating.
Please.
In the lecture notes, Kytela uses always D and then, for example, the law of X on the probability measure. And here you have used interchangeably D before the measure and then distributing it to its arguments. Is this always an equality?
Thank you. It's just the naming yes. It's a convention how you like to use D. So some authors use D in front and some use D inside. They mean the same thing. So they are synonyms. I usually try to follow the notations of the lecture notes, but then sometimes I have trouble because I'm so used to this notation where D is inside. This is the style used in Kallenberg's book, for example. So in this, I'm using the Kallenberg style that, okay, I put the measure and then inside where the integration goes.
Okay, yeah, thank you.
Yes, it's nothing is there, so it's the same synonym. Right, let's summarize. We assume that we have a joint density for two random variables, and then if we do have that, so then we can integrate one coordinate out and we get the densities for x and density for y. So these are now called marginals as well, because yeah, that's what you call a marginals of the joint density. So the marginal densities, yeah. Maybe before a little break, one more thing to look about density. So let's keep this there. Let's assume X has density Fx, and let's assume that Y has density Fy. Okay. Does the joint law, does this have a density as well? And if yes, how to get it? What do you think? Your first intuitive feeling, should the joint law have a density as well? Give me green light if your first intuition is that yes, it should have a joint law. Give me red light if you think that no, not necessarily. It might not have the joint law might not have a density actually. Okay, thanks for your intuitive opinion. It goes actually 50-50, and that's actually how my intuition would go as well in the first place. So it's a 50-50 kind of thing. Maybe it should have a density, maybe it should not have, or what could be a problem. So let's do an example that clarifies this question. Let's first maybe spoil the thing. The answer is no in general. And yes, maybe we ignore the second part because the if yes is not relevant anymore. Why not? Let's do an example. Let's see. Yeah, I drafted some notes for myself, but I think I forgot them at home. So let me think. Yes, let's look at some nice space. Omega with P. Let's make things concrete. Let's think about the concrete omega. Let's take omega to be the real line. Let's take F to be the Borel sigma algebra on the real line. Let's define P of as a probability measure. So if you give me a Borel set in F, so I say that the measure of B is the integral across the real line with function 1 over square root of 2 pi e to the minus omega squared 2 Lebesgue measure on, now I'm using omega because we are in omega now, is this measure. What is this? Well, that's the Gaussian distribution, of course, on the real line. And now the real line happens to be omega. So then let's define x of omega to be omega. And let's define y of omega. Actually, maybe it's helpful to say that this is, I'm using ID to indicate that this is an identity map. And let's use identity of omega. So it means that this is just omega. It's the identity function on omega. Now I have defined then x and y are both random variables. They are defined on this probability space omega fp, and both have values on the real line. Yep. So that's what we have. We could also look what's the law of x. Now if you think, okay, it's the probability and then you have the identity map pre-image of B. Well, the identity is not doing anything, so the law of x is actually just the probability measure of B. It's a bit confusing, but that's how it goes. And if you look at what this is the Gaussian density, so it means that the law of x is equal to the standard normal distribution. So it's the normal distribution with a mean 0 and standard deviation 1. If you look, what's the law of y? Well, you get the same. The law of y is also equal to p, so we conclude that the law of y is also a standard normal distribution on the real line. And we know that the standard normal distribution on the real line admits a density, and this is the famous Gaussian density, of course. What about the joint law of x and y? So now we ask, okay, the joint law of x and y is a probability measure that assigns to every Borel set in the plane the probability. We could say that it's the, let's see how we could say it. Let's see, if we take a rectangle, so then it's you could say it's the probability that x is in B1 and y is in B1, B2, yeah. But now x and y are defined to be precisely the same omega. So it means actually that it's the probability that x is in B1 and y is in x is in B2 as well. Okay, that starts to look a bit strange, but that's what it means. So we could write it that it's the probability that x belongs to both B1 and B2. So we could write it as the intersection of B1, B2. And x is the identity. So we could also write it as the B1 intersection B2. And now we know that it's the Gaussian kernel. So we integrate with the Gaussian density. So it's B1 intersection B2, 1 over square root of 2 pi e to the minus omega squared over 2 Lebesgue d omega, and d means in front or inside, so it's the synonym. So in principle, we now know what the joint law is for boxes. So this is how to calculate the joint law for boxes. And then we know that the boxes constitute the pi system on the Borel-Sigma algebra, which generates the Borel-Sigma algebra of the plane. So actually, by knowing what this measure does for boxes, it uniquely defines the measure using the Dinkins identification theorem. So that's maybe one way to characterize what the distribution in this case is. Or we could also briefly say that the joint law is just we take the Gaussian measure on the real line, and then we take the identity pre-image in this way. Okay, that's the law. It's not very concrete, but that's what it is. Now we can ask, okay, does this law have a density? And I'm actually saying that it does not have a density. Why does it not have a density? Think about this line, which is the, let's take the line x1, x2, or let's write it x and y, such that x is equal to y. So of course we are looking just the line here. Then the probability, then the joint law of the line, well, because by definition x and y are equal for every realization of omega, so then the probability of the line is equal to 1. Okay. What about the Lebesgue measure of the line, the squared Lebesgue measure of the line? And now we think about, okay, we integrate over the line. So we put indicator for the line x and y. We put Lebesgue squared dx dy. And we note again using Fubini that we can write this using two integrals. So first integral of the real line, the second integral of the real line, indicator xy being in L lambda d. Let's take x first and then y. It doesn't matter actually. And we put the inner integral here. So what's the value of this integral? If you look at this, think about y being fixed. And we know that x-y pair belongs to the line if and only if. So we know that, okay, the pair is in the line if and only if x is equal to y, of course. That's the definition of the line. So what's the inner integral? It means that it's the integral of the set where we only have the one point y, and then we integrate with lambda dx. That's actually how it translates to, and then we have integral, and then that's what's inside is the Lebesgue measure of the singleton point, and then we integrate with the other Lebesgue measure here. The singleton point of a Lebesgue measure is 0, so then the full thing is 0 as well. What do we conclude? We conclude that the Lebesgue measure of the line is 0, the two-dimensional Lebesgue measure. Okay. Questions here? If you have, please ask. Otherwise, I want to clean this one. I will clean it. This Fubini helped us to check that the Lebesgue measure, the two-dimensional Lebesgue measure of the line disappears. There's no measure or no mass on the line. And then what? Then what? The claim is that pxy has no density. Why not? Well, we learned that 1 is equal to pxy of the set line. So if we had a density, so then it would be that this is equal to integral over the line, and then using a density. Let's imagine that we had a density. So let me put the red thing. We imagine that we had a density for x and y. And then we would integrate with this two-dimensional Lebesgue measure this way. But now, because this has measure 0, so if you integrate any function across a set of measures 0, so then what happens? It's the same thing as integrating fxy. Sorry about. We need the red color again, so we would need to have the fxy times the indicator of L. That's our function that we would integrate with this two-dimensional Lebesgue measure. This function is now 0 almost everywhere with respect to the two-dimensional Lebesgue measure, and that's why this would be 0. So we have here 1 is equal to 0, so it's a contradiction. fxy does not exist. So this cannot exist. Otherwise, we would prove that 1 is equal to 0. Questions? Let's go here. What did we do? We looked at the random vector, which has something it's a random vector where both coordinates are Gaussian random variables. Yeah. X is Gaussian and the second coordinate y is standard normal distributed. But there's no joint density for this random vector. How does this random vector look? It looks, if you would sample from x, y, so you would sample values on this line. So if I sample a random variable, so sometimes I sample here, quite often I sample close to the mean, which is the 0 here. And sometimes, rarely, I sample here, and I have the one standard deviation there. So approximately, 20-something% I would sample there. So this is how my samples would behave, and they would kind of start to form a Gaussian density on this line, as you see. If you project the line to the x coordinate or y coordinate, you will see Gaussian distributions there. But it's so-called the degenerate Gaussian in the sense that you don't have a bivariate Gaussian density in this case.